Hey there, class. Mr. Moynihan here with a U substitution problem. We will learn over one of these in class, but I thought it'd be worthwhile to re-examine the procedure here. So right now, this radical might be obscuring some things, so let's rewrite the problem slightly. So 5x times the quantity 3x plus 2 to the 1/2 power dx. Now it looks a little more familiar. The question to ask is, can I apply the reverse chain rule, which is to say, is the derivative of the interior sitting next to it, or is it a constant multiple away from sitting next to it? Well, the derivative of the inside is 3, right? Just 3x plus 2's derivative would be 3. And I don't have a 3 next to it, nor do I have an easy way to get a 3 next to it because of this pesky x term. So I do not have an opportunity to use a reverse chain rule. So what that means is I must use U substitution. So I'm going to let U equal the interior of my problem, which is 3x plus 2. So this is the key part. I'm going to make this assumption, and then I'm going to take away some consequences from that assumption and allow me to rewrite the problem in terms of a different variable. So this implies, right, this is the same thing as saying that U minus 2 is equal to 3x, right, just solving for x essentially. Moreover, what that means is that 1/3 U minus 2/3 is equal to x. If you're not comfortable with that, then perhaps you might say U minus 2/3 is equal to x. These things are equivalent. So what that means is I have a way to interchange U for x and likewise x for U. So that's one consequence of this assumption. The second assumption is that I can also change my variable of integration. I'm taking the antiderivative in terms of x, but I'm going to turn this into a U problem, so I need du's here as well. So if U equals 3x plus 2, and if I take the derivative with respect to x on both sides, then du dx, well, the derivative of the right-hand side would just be 3. And I'll multiply both sides by dx. So this is a process called separation of variables, and therefore du is equal to 3 dx. I'm going to solve for dx, thereby replacing dx, and thus dividing by 3, du over 3 is equal to dx, or if you prefer, 1/3 du is equal to dx, they're the same expression. So this assumption creates these two consequences, and I've given some alternate forms in case some of these are more preferable to you than others. All right, so let's look at the problem and see how we can rewrite it. 5x, right, which is what we had as our first section here. The 5 I'm not going to replace, but I'm going to replace the x with, well, it looks like this is U minus 2 quantity divided by 3. So that right here is simply what x used to be, right? Then I had the interior, which is 3x plus 2, and I'm, by definition, replacing that with U, and that's still raised to the 1/2. And this part here used to be called dx, but it is now called 1/3 du. So hopefully you can see that piece by piece I've replaced them and replaced all of my x terms with U terms. Okay, well, what good does this do us exactly? Well, let's find out. I can combine the 5 here and the 1/3 there slightly to simplify it a bit, so that gives me 5/3 times U minus 2 over 3 U to the 1/2 du. I can go ahead and distribute, well, multiply essentially, so that will give me, let's see, 5 U minus 10, right, if I multiply the 5's on top, and then 9 on the bottom, 3 times 3, times U to the 1/2. So this stuff makes this. I still have integrating with respect to U. I'm going to break this down slightly. I'm going to write this as 5/9 U minus 10/9. So I'm basically breaking down this into two pieces, because I'm dividing both of them by 9, and I'm multiplying by U to the 1/2. Now some of these just come down to preference in terms of how you like to take antiderivatives. I like to have all my terms separated, that way I can use the power rule all at once. So really all this stuff here is just a little bit of simple algebra and rearranging things so it looks more familiar by using the reverse power rule. Finally, I'm going to distribute this U to the 1/2 to both of my interior terms, giving me, if I watch my exponents carefully, this is a U to the first power, thus U to the, when you add the exponents, 1/2 or 3/2 power minus 10/9 U to the 1/2 power du. So now you notice you have things essentially ready for calculus, by which I mean they're sort of in this form, coefficient, variable to an exponent, right? So when you have this form, you're ready to use the power rule, whether for derivatives or integrals, frankly. So let's take the integral of each part. 5/9 is a constant multiple, so I'm still going to have it here. U to the 3/2, using the reverse power rule, is adding 1. So adding 1 to this will make plus 2 over 2 makes 5/2. And I'm going to divide by 5/2 using the power rule in reverse. 10/9 constant multiple, excuse me, u to the 1/2 plus 1 gives me 3/2, and then divide by that, plus constant c. Now effectively this is our answer. It can be cleaned up significantly, however. So I have 5/9 out here. Dividing by a fraction is the same as multiplying by its reciprocal, which is to say keep it, flip it, change it, if you remember that from roughly 4th grade. So that's this part right here, u to the 5/2 minus 10/9. Likewise, this becomes 2/3. U to the 3/2 plus c. I can simplify, and this gives me 2/9. U to the 5/2 minus, let's see, I can cancel here, minus 20 over 27, u to the 3/2 plus c. And that looks a lot cleaner. However, this is these are in terms of u. Remember, u is simply an expression of 3x plus 2. So I was given an x problem. Let's return it back to an x problem. That becomes 2/9 3x plus 2 to the 5/2 minus 20 over 27 3x plus 2 to the 3/2 plus a constant multiple. And believe it or not, if you take the derivative of this bad boy, you will get the nice humble problem we started with, which if I zoom out, we can see all at once, was back there. This can also be rewritten in some other forms, but frankly, that's good enough for now.